So thanks a lot. Thanks a lot for the introduction. Thanks for the invitation. I'm very happy to be back here and to enjoy the place and also the talks, of course, and the discussions that happen also outside of the talks. So many thanks again to the organizers for setting up this event. I really enjoy it. I would like to talk about interacting particle systems. So the title is not very explicit, but I should say right away that I'm not going to try to address every possible interacting particle system that you can think of. So there will be some assumptions that I have to introduce. And to say it very briefly at first, the particle systems that I want to consider, they are particles that live in RD, and they have a density in RD. They are kind of dense in the plane or in the space. And they interact with one another in a short-range way. Okay? So typically, one particle will see a couple of other particles in its neighborhood, and this is what will affect its behavior. If you remember the talk of Maria Bruna, this is going to look very much like those particles, but without this active-passive distinction. In some sense, maybe all my particles are passive. I don't know. So each of them is going to try to do its own Brownian motion, but will be influenced by the neighbors around. And for this sort of particle systems I want to describe, it has been known for quite a while now that over a large scale you can capture their behavior via some sort of partial differential equation. This is well understood. But what I would like to try to explore during the talk is whether we can make this quantitative. Can we say how good this approximation by a partial differential equation is? Can we say if I take a scale very large but finite, the error I make in my approximation is not too large by this sort of amount? Okay, so I'll have partial results about this that I'm going to try to present. And these results are based on joint works with Arianna Giunti, Chen-Yin Gu, and Maximilian Nitschner. So I would like to also consider other models. So at first, I'm going to spend a bit of time making sure that we are all comfortable with these different models and how the specific one I want to discuss is defined. And I have to say also that I have spent most of my research time thinking about other problems that particle systems. In particular, before considering particle systems, I worked for quite some time on random walks in random environments, or if you prefer PDEs, in divergence form operators with random coefficients. So this is kind of always in the back of my head, and maybe not just in the back of my head, also maybe sometimes in the way I speak about stuff. So I'm going to say a little bit about this. But of course, my goal is to discuss also interacting particle systems. And for the sort of models that I want to discuss, the recent literature at least is mostly on discrete models. So particles living on ZD. But for some reason, I feel more comfortable with models defined in the continuum. So if you're not a specialist of particle systems, maybe you're a bit more indifferent. But if you are, then I'll try to explain the connection with more standard models in this setting. Okay, so basically I spent more time working on these sort of models in the continuum. The more standard thing for particle systems in the discrete, but today I'm going to use particle systems in the continuum. And but still, okay, different things will appear as we go along. So in order to define my particle system, I'm going to kind of try to introduce it by making an analogy with these random walks in random environments. I'm going to say we're going to try to build it so that it resembles the random walks in random environments that I already understand a bit better. So let me discuss this briefly. So let's say you're in ZD. I'm doing the discrete version for now. And so at first you give yourself a random environment. And we can encode this by deciding for each edge on the lattice you pick a random number W, so omega E for edge E. And this number is going to tell you the jump rate for your random walk to jump across the edge. Okay, and the important property I want to have is that I think about the edges as being unoriented. So the jump rate from this side to this side is the same as the jump rate from that side back to this side. Okay. So this is the reversibility property that I'm going to enforce in all models that are going to appear in this talk. So if I think about this edge as these 2 points x, y, I want this property to be valid. Okay, and then if I write the generator of my random walk, it's going to look like this. So sum over, so if I look at it evaluated at x, I sum over neighbors of x in my graph, which I write like this, omega xy, f of y minus f of x. Okay? And okay, we can also think about the energy function. I'm going to talk about this in a second. This is the discrete version. If we do the continuous version, I'm going to want an analog of these coefficients on the edges, which is going to be a function from Rd. So now I'm describing the continuous version of this. Okay, this was the discrete version. From Rd to the space of matrices, symmetric matrices, let's say. And instead of writing this, here I'm directly writing the generator of the object because it's kind of simpler to describe, in my opinion. And the generator I want to write down is this one. So why do I say that this is a good analog of the discrete model? It's because in the discrete model, so oftentimes this is called the random conductance model also. In the discrete model, we had this property. Okay, so this meant that the counting measure is reversible for the dynamics. And the analog in the continuum is that I want to make sure that the Lebesgue measure is reversible for my dynamics. And that means that I can do some integration by parts. Okay, and this is the structure that I need to do my integration by parts when I do this calculation. Okay, so here the Lebesgue measure is reversible for the dynamics, if you like. And just as a reminder, when you consider this operator, associated with it is an energy function or a Dirichlet form, which is just grad f dot a grad f that you integrate over the domain you care about. Okay, so these are the objects that are natural in this perspective. And of course, you need assumptions on A, which I have not discussed, but just to set up the notation. So far, so good. If it's okay, I move to particle systems. So now I would like to imagine a particle system that looks like this in the sense that I have a bunch of particles, and each of them, in a sense, is trying to do a motion like the one written there, except that these coefficients, either the omegas on the left in the discrete, or the A on the right, they are not given in advance. They are just computed locally according to the positions of the particles around. Okay? So let's say interacting particle systems. So I will have a family of particle positions. Let's say an infinite number of them. I'm going to index them by the integers for now. And t is greater than or equal to 0. Okay, this is my family of particles. And perhaps I don't immediately write the definition, but if you imagine your situation in the lattice, it's really analogous to what is above. When you freeze a configuration of particles and you look at one that is placed here, and you ask yourself, what's the probability that it jumps to the right? This time it's going to be a function of the particles around. And I always want this property of reversibility. Okay, so let's say now this move happens. If I ask myself, what's the probability that, given that the rest has been kept frozen, what's the probability that the walk comes back to where it started from? I want that to be exactly the same. Okay? So perhaps I'm not going to try to write down the definition in the discrete, but for those who know these systems, oftentimes it's, I think it's called lattice gases, or maybe generalized exclusion processes, or generalized exchange dynamics. It goes under various names. But now let me try to imagine what would be a continuous version of this particle system. So now I'm looking more towards the right side of the board with this generator. And let me see if I have a good way to. So let's say in the continuum. So we would like to say that at a given time, let's say if I fix a cloud of particles and the time, and I ask myself what this ith particle wants to do, I want to say that, so this is an informal description, okay, but wants to do a diffusion with diffusivity matrix. Let's say A naught of. So I'm going to, okay, so maybe I should have said that before. So this function. Okay, so perhaps I should have taken a couple steps before, but I want to think about my particles as being indistinguishable. So in fact, I'm not going to keep indexing them like this all the time. I'm just going to keep track of the measure that they generate. Okay, so instead, I'm going to write like mu bar t like this. I hope I'm not going to forget the underscore, but it's just the sum of the Dirac masses of the particles. Maybe I will check. Okay, and in truth, I'm going to think that this is my true process, okay, this measure process. I'm going to forget about these indices, but just to facilitate intuition, I introduced it for now. And now there is this fixed function, A naught, which I give myself in advance, which describes my model. And that particle indexed by I is going to look at what happens around it and look at this diffusion matrix computed according to the position of the other particles, and do a diffusion with this diffusivity matrix, sort of in the sense of what is on the right side above. Okay? So if I try to be a bit more precise, so let's say generator for n particles. The harder part of my talk is to get used to the model and notation. Okay, so we have to kind of. So if I imagine I try to keep track of n particles that move around in RD, I'm going to say that this is the sum of these divergences on each of the coordinates. So xi, each of these guys lives in RD, right? Okay, so you have an n tuple of components, each of them being in RD. Okay, and maybe I don't rewrite all of the coordinates. Does that make sense? This is my generator. So I think I'm going to want to introduce better notation to keep track of this. Okay, better, at least notation that I prefer. And so I'm going to do this measure thing first. Okay, I no longer want to keep track of the indices of the particles. They are indistinguishable. I don't care if their number is 3 or 17. So let me write mu, this sum of Dirac masses. I just try to put an underscore when I think of this as the Markov process. But if it's just a measure, I don't put the underscore. Okay. Mu is this. And then, so there's this A naught of mu, which I give myself. And then maybe I want to write A mu comma x, which is, well, basically this object, which, so A naught of mu translated by the vector of x. Tau, maybe I'm going to define it under, sorry. A of mu comma x, A naught of r minus x mu. Okay, so that instead of writing this big thing, I can just write a of mu comma xi. Okay. Yes?
So the mu is not normalized, it's not a problem.
That's right, it's not a probability measure, in particular because it's convenient for me because later the invariant measure for my dynamics is going to be this Poisson point process. And so I want to have points kind of everywhere in space, and so this will not be a normalized measure. The total mass will be the number of particles, possibly plus infinity, yes.
What kind, can you have the Dyson-Brownian motion?
The Dyson-Brownian motion? So I don't remember if it's in divergence form, so...
What kind of model?
Say again?
What kind of, classical dynamic can you cover?
I don't know many classical dynamics, so I don't know if the Dyson-Brownian motion... Sorry? For me, this is the interacting particle system analog of this divergence form operator in the regular space, and I find it very natural. But I don't know if it has been considered a lot. Okay, there has been some papers a while ago with Albeverio, Rockner, and others considering this model, but overall it has not received a huge amount of attention. But the discrete counterparts have been studied significantly more. By people studying interacting particle systems. But I'm not confident that Dyson-Brownian motion is fitting into this framework. Other questions? Like in particular, it's a short-range thing I'm going to consider. I haven't stated the assumptions on this function yet, but for now I'm going to think that this is short-range. Perhaps one natural model that you could think of, but which will ultimately not enter into the assumption I'm going to make, is just that around the points you imagine that there are little balls, and you just say that they don't want to overlap, okay? And then they do their Brownian motion, and then they just bounce around. Now this is more difficult to study because you have this exclusion rule. So in my model, I will allow things to also overlap because you have to start with the simplest possible thing, and that's what I'm going to do. But this is perhaps the most natural model. Other questions? I like very much to have questions, so please. So yeah, it's going to be a fixed function. So for instance, you can say it's the identity if I don't see particles around, and it's twice the identity if I see a lot of particles around. For instance. Okay, and yeah, so the second thing I want to do about notation is to introduce notation for this gradient. So instead of thinking of f as being this function of these n variables, I want to think of it as being a function of the measure. In particular, allowing the measure to have possibly n or n plus 1 or different numbers of particles. Okay, so it's just a function of the measure. And for each point in the support of my measure, I can compute a gradient by doing the obvious thing. Okay, I just move around the Dirac that is sitting at x, and that allows me to compute a gradient. And that is going to be gradient f at mu comma x. Okay, it's a sort of transport derivative if you like. But if you think back in terms of these coordinates, this is going to be grad f mu comma xi. Sounds good? Okay, and then you see that we are summing over all points xi. So these are the points in the support of the measure. So instead of writing this sum, I'm going to fancy to write it as an integral against the measure mu. Okay. Oh, maybe I can still squeeze some stuff. So if I was writing the energy function also, which I like perhaps even more than the generator, if I was using these coordinates, I would write something like this. Maybe I'm not going to write all of the arguments. But then in the notation with in this other notation, it's going to look like integral of grad f of mu comma x dot a of mu comma x grad f of mu comma x d mu of x. Okay, and sometimes I like to write this simply as integral of grad f dot a grad f d mu. Okay, but I stress that this is a slightly misleading notation because I write an integral, but this really denotes a summation. So in particular, just using this integral symbol, you cannot do your integration by parts, okay, which is the tool I know how to use. So just so you know, yeah, at this stage, you cannot yet do integration by parts, unlike what is written on the top board with the model in RD. So I already said that the invariant measure for this so sorry, not the invariant measure, but a family of invariant measures are all the Poisson point processes with a fixed density, and I'm going to write like this to denote expectation with respect to the Poisson point process of density rho fixed. Joseph, you seem to be you're okay with that.
Could you repeat the definition of grad f u comma x?
Ah yes, thanks. So you maybe I can write it more explicitly. So that's why you take the Dirac at x and you move it a bit. So maybe if I was writing it explicitly, let me project it onto the case coordinate. That I take a limit epsilon goes to 0 of oops, sorry, maybe. So x is in the support of mu, and so I can subtract the Dirac, okay, and it's still a non-negative measure, and I just replace it a little bit shifted, okay? And I divide, and that's the definition. Sounds good.
Can you explain this comment about the integration by parts? Because it seems like you kind of did integrate by parts to go from what you have on the top.
So I didn't say that they are equal. I just said this is going to look more like the energy function, and I'm going to keep it. But for now, it's not. There's no direct relationship between the two until I do also my expectation with respect to the Poisson point process. Thanks a lot for this comment. Yeah. So okay, it was just to get comfortable with the notation. I did that, but. So now the energy function really for my model is not indeed what is written above, but that same thing integrated also with respect to the Poisson point process measure. Okay, and the integration by parts thing which I'm kind of looking for is coming from the expectation, in fact. Okay. So it's true that f multiplied by LF integrated is equal to this energy function, but the integration it's that thing that is doing the work. Okay. Other question? Okay, so I'm not going to discuss how you actually construct the stochastic process, but if you want, we can come back on this later. But you can build a stochastic process that kind of matches the sort of intuition I'm trying to convey. And this is the stochastic process I would like to study. So I didn't say what assumptions I would like to enforce. So I described informally these balls that don't overlap, but this I'm going to now exclude. So we have this function a naught, which takes as an argument some point measure and takes values in these matrices. And I want it to be uniformly elliptic. So let's say there exists a lambda such that for every measure I choose, this is true. Okay, and this is true in the sense of PSD matrices, or if you like, you can think of this as just being a scalar, and it's between 1 and lambda. Okay. No problem assuming this is a scalar. This is the first assumption, and the second assumption I mentioned at the very beginning, I think, is that this model is going to have, these particles are going to have short-range interactions. So when I want to compute my diffusion coefficient in some cloud of particles mu, it suffices that I look at this cloud of particles in a ball of a radius, let's say 1. Okay, let's just put 1 just for convenience. Okay, I use the same notation as in Michael's talk. This is you take a measure, you restrict it to a set, and B1 is the unit ball centered at the origin. Sounds good? So these are the assumptions. Okay, so under these assumptions, so this model specifically has not been considered for the results I'm going to mention now, but the discrete models that I did not fully define have been studied a lot, and they are really closely analogous. I assume the results could also be proved. The results I want to describe now are this large-scale behavior, the hydrodynamic limit, and the behavior of fluctuations. So let me try to describe this. So maybe you want to first give yourself a density profile rho naught. And let's say for definiteness that you run your dynamics in a box of size n, maybe with periodic boundary condition, okay, just to fix something. So then your density profile, you rescale it to the size of this box of size n. So you're going to take a look at it like this. And then you study this dynamics. And you also, so you rescale, so then let's say rescale space by n and time by n squared. And you look at the evolution of the density of particles. And what you discover is that in the limit, the density of particles is described by, like its evolution in time is captured by this PDE. Maybe I'm going to write subscript t each time so that we keep in mind that in this part rho is not constant. Okay, so it satisfies a sort of heat equation with an effective diffusion matrix, A bar of rho, which you can express separately. Okay, it doesn't have an explicit form, but you know it exists and you can describe it in some abstract way. Okay, so for some A bar. For some function A bar of rho. And that function A bar does not depend on the initial profile you take. It's just for every trace. So maybe I should cite some references. I think this for the discrete models, yeah, actually this showed up in the talk of Maria. Was proved by Varadhan and Quastel, and by Funaki, Ushiyama, and Yao with a different method around in the 90s. So in this talk, I'm going to focus on another result, which is entirely at equilibrium. So this was the only part when the density is changing. Now density is fixed. That's it. Density is not going to change anymore. But even at fixed density, you can ask yourself interesting questions about the evolution of the particles. So let's say fluctuations. Okay, so let's say you start at equilibrium. You start at this Poisson point process with density rho. Then this is a very well understood process with as much independence as you can imagine. So if you just want to understand the scaling limit of the initial condition, it's very easy. And this is preserved over time. So at any given time, you know exactly what's the scaling limit of the distribution of the particles. But one thing you can ask, which is less obvious, is how is the time correlation? How does this evolve over time? And that's the goal of this consideration. So how to set it up nicely? You could decide that you're going to try to focus on the. So this is my cloud of particles encoded by this measure mu, which I look at time n squared t. I had put in parentheses. Maybe I'll keep at the index for the time. Okay. So this is the cloud of particles at time n squared t, and I subtract the average behavior, which is basically flat with density rho. So rho times the Lebesgue measure. Let me write m for the Lebesgue measure. And I rescale in time also, in space also, sorry. So this is the object I would like to understand when n becomes very large. So if this notation feels kind of confusing to you, you can think that it's a distribution, and if I test it against f, then what I get is n to the minus d over 2 integral of f of x over n d mu n squared t of x minus rho integral of x f x over n dx. Okay? So as I said, if you want to understand how this behaves for a fixed t, it's kind of trivial. But you may try to understand the joint behavior as t varies. So let's say a theorem. Well, okay, it's not really, it has not been proved for this model, so I'm not going to write theorem, but it's highly plausible that as you rescale, you converge to something, which I'm going to denote y infinity t. Let's say in some space of distributions, you take a sufficiently reasonable space of distributions, and that will be true, where this you can give an explicit description, and it solves this equation. Where psi is a space-time white noise. So before I was writing a bar of something in the previous statement, but from now on I told you that the density will be fixed at rho. So this is really just a bar of rho, but I didn't write a bar of rho. Okay, I just wrote a bar. Oh, so this is and the initial condition for this guy is the white noise with density with variance rho, okay, because this is the reasonable thing you have to take because of this Poisson point processing. So this is a pretty sophisticated way to say that, in fact, what you observe is the same as if you just take, so you have your cloud of particles with density rho, and each of them is doing their independent Brownian motion with covariance a bar, and is just not caring at all about the others. This is going to be the process you observe. Okay, so this is a way to encode that in this limit, the fluctuations you see are just the same as if the particles were behaving independently of one another with this spatial matrix A bar. Does that make sense? Yes.
So this is also in the weak sense of mind? Why is the measure?
Yes. So I mean, space-time white noise is a little bit singular, but this is a linear equation now. So you can decide that you write the heat semigroup for this thing. You write it in some Duhamel style, and it's not very difficult to make sense of this because it's just linear. That sounds sensible. And finally, I'm going to state a kind of a shadow of this statement, which is going to be my focus, which is the behavior of correlations of this object as n becomes large. So in particular, well, okay, depending on the topology you choose, it's not obvious that it follows, but at least it follows from the proof. Limit if I look at my object ytn here tested against some smooth function f, and y0 tested against some other smooth function f, then in the limit of large n, it converges to whatever it is for the limit object. So let's say it tends to no, it's just an abstract object, so like this. And this object is a bit intimidating, but I told you it only means that the particles are just going independently of one another without looking at one another. So it's easy to write an explicit formula for what that is. And so let me write it, which is rho times integral f of x psi t x minus y g of y dx dy, where this is the heat kernel for the operator with the a bar. You can write a formula for it, but maybe I'm not going to write. But it's just exponential minus x squared over 2, except you insert a bar somewhere at the right place. Okay?
A bar depends only on rho, not on...
That's right. A bar is only a function of rho, but from now on, we think that rho is fixed. So a bar is just a fixed matrix. That's it. I didn't tell you how I find a bar, but I'm going to tell you how to find a bar. All good?
Sorry.
Yes.
So in the previous upper right board, the A bar of rho is rho. It only depends on the point-wise evaluation of...
That's right. That's right.
Really?
Yes. Yes, it's just it's a good question indeed, but when you work out the proof, you manage to squeeze a mesoscopic scale where you already can do the calculation for the density, and then it's okay. And in some sense, my talk is about how do you measure this mesoscopic scale? How do you make sure it's, when you do the qualitative proof, you can just barely show that it's a bit smaller than the scale you care about. But now, with the sort of things I'm going to describe, you're going to be able to squeeze some little, distance to some power inside this thing. Yes. Eraser. Okay, so the statement that is on the left, this covariance converging to something, is the statement that I'm going to present a quantitative version of it. So for now, yeah, there will be, okay, the rate of convergence is not as good as it could be, but hopefully in the long run it will be possible to improve it. Where am I? So now this time it is a theorem. Oh, I didn't say, but this result on the left was not proved for the specific model I described, but was proved for the discrete models by Liu, and also by Cheng, and also by Funaki in slightly different models, also in the 90s. So this is a result with Chenlin Gu and Maximilian Nitschner. And the hard part of the proof is from another paper which was also with Arianna Giunti. So the claim is that when you compare this covariance thing on scale n, with what the limit should be, you get an error which is at most a small power of n, n squared t to the power minus alpha. Okay, is the statement clear? So I write it like this because, in fact, there's a scale invariance in this statement. So if you just write the statement for n equals 1, you have it for every. So you can think that this is just a statement for n equals 1.
Your notation for E mu 0 bar, I think you had it for E rho, but
Ah, yes, thanks a lot. I did not say it and I forgot. Thanks a lot for the question. So this, I mean, when you average over the behavior of the stochastic process, starting from the cloud of particles mu naught. But so this is, you pick a random initial point cloud, and this is, you do your evolution of your Markov process starting from this point cloud. In practice, the tools that are going to appear in the proof are mostly, let's say, PD flavored. And so in some sense, this expectation is going to disappear. You know, I'm going to just think this is so this function with the inside expectation. I'm going to think of it as a solution to some equation. And so in the end, that's why I kind of split it up, because in the end, we mostly only work with this expectation, and this one quickly disappears in some sense. Does that make sense? Yeah, it's really, you throw your point cloud and you put Diracs at all the points of the point cloud, and this is mu naught. This is your initial configuration that you run. All good? So we wrote another result which I'm not going to present, but it's you can write a Green-Kubo formula for A bar. And this also, at least for other models, was understood. But now we can say that if you localize it in time and space, you make an error of so and so. And so, as I already started to mention, the starting point of the proof is to think of is to look at this function, let's say, which takes a time and a point cloud and gives you the expectation over the Markov process only of, let's say, f of mu bar t. This function is going to solve a natural partial differential equation. So let's say PE. If you think about the first models I described at the beginning of the talk, this random walk in random environment, This would be just my random walk. Let's say if you try to make the analogy, and then this would be solving some sort of heat equation with the random coefficient. And in this case, it's going to, so let's say looking like a PD looking like. Okay, it's going to look like this, but remember that now our operator is taking all the particles and moving them around. So it's this is acting on functions that take many variables together, and the A is just a function of some of these variables at any given point. Okay. And then I put the title homogenization inside the. So I put the word homogenization inside the title, and perhaps it's not very common for this topic, but by analogy with what we understood for other systems, it felt like it made sense. And in the context of random walks in random environments, or like these divergence form operators with random coefficients, what we did first is when we wanted to understand the homogenization properties of this thing, it was very helpful to first focus on the study of some energy quantities, which are in some sense analogous to those that appeared in the talk of Michael on optimal transport, which will have also these subadditive properties and will be more convenient to understand in more detail first. And once you understand these objects, you can do two-scale expansion, say that locally you can use this to approximate the solution and, let's say unroll a kind of machinery that propagates the good things you understand on the simple question towards more complex functions. So to introduce these quantities analogous to those of Michael, I'm going to just write them. So it was helpful for us to try to use notation that looks as much as possible like the one for random walks in random environments, like in this, because then it was easier for us to identify what the right quantities were. So now the notation is so good that you don't even realize you're making an effort to find the quantity, because you just write the same thing as in the previous problem, and it's sort of the good quantity. But it turns out it actually took us quite some effort to understand that this was correct, and that we could indeed work our way around these quantities. All right, so what did I write? I wrote this, infimum for V. So first, what is this thing? This is just a cube in RD, a cube whose side length you decide. P is a vector in RD. And I'm looking at this optimization problem. So I wrote the energy function that I claim is very central to the definition of the model even. And I try to optimize over all functions that kind of try to look like this function LP, comma cube, which I'm defining now. This is just the function that kind of counts the slope of the, like for each particle you count what is P dot that particle and you sum over all of these things. Okay, so in some sense when I try to make analogies between the world I know of random walks in random environments and the world of particle systems, I try to think that at least in some large scale and vague sense, the typical functions will look like a sort of simple function that is analogous to the one I was seeing for random walks in random environments, which I then sum over all the particles that are moving around. Okay, so this is my, let's say this is our basis for what is a function with slope p in this world of particle systems. So in particular, if you compute the gradient with my strange notation, you see that each time you move one of these particles, you get p. Okay, so this is really the function that has constant gradient equal to p. Did I make a mistake? Sorry. Ah, yes, thanks a lot. Okay, and this H10 cube, maybe I'm not going to write the definition because time is running short, but it's any function that essentially only is allowed to look in the interior of the cube. So for instance, counting the number of particles in the cube is not allowed because this you have to look up to the boundary of the cube. So the functions that are in this space are such that if you have a particle sitting in the middle of your box and you bring it to outside the box, then this is a continuous move. Like there's no moment when the particle leaves the box and boom, you have a transition to some other value. Okay, so in particular, if A was constant, the best choice you can make for this optimization problem is just to take V to be equal to LP. And when A is not constant, this guy which is going to live in this space is going to be correcting for this thing. Okay, so over large scales, in some weak sense, our optimizer wants to look like this function LP. And this kind of helps you to measure how far it is from being that. So like in Michael's talk, this quantity has a nice subadditivity property because I told you that this function here is such that it only looks in the interior of the cube. So in particular, if you take different cubes and you have candidates that look inside the interior of each cube, you can kind of patch them together and it's a function that looks in the interior of the big cube. Okay. So and in fact, subadditivity, here we have to take expectation over everything. So it doesn't really even, if I look at a cube somewhere or a cube of the same size somewhere else, it's just exactly the same value. So perhaps instead of subadditivity, I should just say that this is going to be a monotone sequence as I vary the size of the cube, at least over a dyadic scale, let's say.
The L actually doesn't depend on the box, on the square.
It's just that, yeah, I should have, I sum over, like otherwise it's an infinite sum, so I sum over the domain. Yeah, I had forgotten to write this, but it's a bit scary. Okay, to avoid, I want to have a function that satisfies this, and you could really think that it doesn't depend on the domain, but then just to write something definite, I write. Say again?
Let's be only if X is inside the domain. That'd be great.
Is that in fact the measure here? I really sampled the measure in the whole space a priori. And it's actually not purely pedantic because the A is going to look a little bit outside also. So I have to have a little bit of particles sitting outside and doing something here. Yes, and my time is now running short. But one comment I wanted to make is that, yeah, once you notice this monotonicity property, well, okay, so I should say also that it's also not difficult to see that the optimizer in this problem is going to depend linearly on P, okay, because it's quadratic inside the energy, and okay, it's a simple reasoning. And so in particular, the energy function as a function of P is going to be quadratic in P. So you can define a matrix. So define a bar of cube. So that nu of cube P equals 1/2 P dot a bar of cube P. And yeah, by this monotonicity argument, a bar of P is going to converge to something. And that something is my a bar. Okay? So this is the definition of a bar, finally. I was a little bit worried. I said I would give you the definition, but I did manage to make it. And the thing that we had worked out with also Arianna Giunti before is to get a rate of convergence for these objects. Like how fast does this guy converge to this guy? So okay, maybe I don't have time to write it, but just we got a rate of convergence, like some small exponent exists, such that the difference between these two things is at most the volume of the cube to the power of minus alpha. And this is the ingredient we use in order to prove the theorem that is above. Why is it useful? It's because indeed once you know that this convergence, you know the size of the object that is living here and is correcting for, in the large scale limit, you expect that your function wants to look like this. And this is this correction term. And it tells you that this correction term is not too large. Okay? And once you know this, you can use it in many circumstances, for instance, in here, or when we wanted to specify a bit more about this Green-Kubo formula. Let me try to stop writing and just say 2 more words. So at this stage, it's also perhaps not extremely satisfying that the exponent is not explicit. But in this other context of divergence form operators or random walks in random environments, this was actually a necessary step for us to get into obtaining better rates of convergence. So, as has turned out, interacting particle systems have been rather difficult to handle. Like it took us a significant amount of time to work this. So I cannot claim for sure that this same program can be applied in this case, but at least there is a plausible candidate route, let's say, to improve these rates once this is better understood. So maybe on this, I'm going to stop. Thanks for your attention.